Good morning, everyone. Welcome. It's early here. So without further ado, I'm just getting myself organized. Let's go to chapter 3 of Principles for Building Resilience. We're looking at page 50, in effect. This chapter is devoted to a discussion of redundancy and diversity in relation to our general conception of resilience. They say as much on 51 that the chapter will look at the relationships between diversity, redundancy, and resilience. So we should keep in mind here two things, two parts of our general context. One is, of course, the idea of resilience itself, which this book is an effort to explicate in some detail, to explain, that is, in some detail. We have also seen the notion of a complex adaptive system. We've seen the notion of a social ecological system. And these authors contend, they argue that a social ecological system is in fact a complex adaptive system. So that's where we've been. We talked in the last reflection 6, I think, about the political dimensions of this entire picture. I expressed a few doubts about how well the political dimension fits into the notion of a complex adaptive system. But let us put those aside for now and turn to the concept, first of all, the concept of diversity. I think the authors give us a pretty helpful definition of it. And I must say, when I sit down and ask myself, what do I mean by diversity? I'm not sure I would touch on the three elements the authors mention here and describe. So I thought it was helpful to run through this. So when we talk about diversity within a system, what in fact are we talking about? According to the authors, we're talking about three things. First, we're talking about variety. So how many elements does the system have? Second, we're talking about balance. How many representatives of each element? So how many elements and how many kinds of each element, right? And the third element, and this is the one, I think it's obvious, but I would have overlooked it, the element of disparity, how different the elements are from one another. So what's the degree of difference? It's almost in a statistical sense, a degree of freedom, but forget about that. It's take it as a degree of difference. So how disparate are the elements is the question of disparity. How different are they? Now, without further ado, oh, by the way, they provide all sorts of examples of diversity in complex adaptive systems. In the example they use is plants. But, you know, let me expound on that a little bit. Much of this, much of the notion of resilience, it comes out of, and I mentioned this, I think, in the last reflection, it comes out of biology. These are properties of organisms. Organisms regarded as complex adaptive systems. So is it a surprise that we're talking about plants when we want to illustrate diversity? We could take this a little bit further. What is it about the plant? Well, it has a genetic inheritance, and inside that gene pool is an immense amount of diversity. And there's diversity not only with respect to the specific genes, There's diversity with respect to their combination. So this, I think, is what these authors are thinking of in an indirect way. When they think of diversity, they're thinking of how organisms maintain gene pools that also have mutation inside them. So the genes are not only different, they change over time, they mutate. And because they mutate, the organism has a much greater diversity of response, right? It's far more capable of responding to changes outside itself. Now, so I think that idea is always lingering in the background here, that notion of a complex adaptive system as represented by an organism, a plant, for example. So it's not surprising their examples refer to organisms. It's what I think you would expect. Now, let's go to redundancy. It's a different notion. Redundancy describes, and this is a quote, by the way, on 53. Redundancy describes a replication of elements or pathways in a system. Now, let me expound on that too. Why does redundancy matter? Well, if I have a pathway to a response, call the response X. So the response is to a change in the environment outside the organism, right? So the organism has a response X to an event in its environment. If it's capable of providing a pathway to the same response through a different pathway, and if it has, say, a third or a fourth pathway, then if the first pathway is somehow shut down, the organism can revert to the second pathway. If that pathway is shut down, it can revert to the third. So you can see how redundancy of functions can supply the organism with versatility and agility, right? Because it has more than one response to an environmental change. This will matter a great deal when it comes to the notion of a tipping point, or what the authors here call keystone elements. Now, I'm reading into the text a little bit here, so I would want you to be aware of that. But as I see it, the idea of these tipping points, of what they call keystone elements in a system. Keystone elements, you know what a keystone is, I hope. I'm not sure I know what a keystone is now that I think about it. A keystone is, if you have an arch, it's at the top in the center of the arch. It holds the different parts of the arch together. If you pull it out, the arch collapses. So these are elements that are pivotal to the survival of the system. So they have greater importance to the survivability of the organism than other elements. So you would regard them as keystone elements. And I think they're related in ways that we'll talk about down the road to what are called tipping points. In fact, I think they even have a kind of model of a tipping point here on page 62. But I don't want to go into that right at the moment. What I wanted to talk about, because I think it's quite important, is we need to recognize that while diversity and redundancy are pivotal to the complex adaptive system, although they're pivotal, they are subject to certain limits. And all I mean by that is too much diversity can hinder an organism. Too much diversity can prevent it from functioning. And likewise, too much redundancy can render the organism inefficient and can lead to its ultimate demise. So too much of a good thing is a bad thing, both for redundancy and diversity. So I would urge you to keep that in mind. Now, on the general question of why do redundancy and diversity matter to resilience, I think the relationship should be pretty clear, and I suspect in your own minds, it already is pretty clear. But just to map it out in one statement, I would say this: resilience is about the ability to respond in a useful, effective, and efficient way to change. That's what resilience is for now. We may refine that notion, but for now, let us see resilience as that ability. It's the ability to respond to change and to respond to it in such a way that you maintain the health and welfare, so to speak, of the organism, of the complex adaptive system. Now, that's what resilience is for now. Redundancy, I think its role in advancing resilience is clear. If you have no redundancy in the system, you have one pathway of response. So you have no agility. You have no ability to pivot or turn, right? If your principal pathway to response is harmed or damaged or removed, you're done. Your goose is cooked. On the other hand, without diversity, you lack the organism or the system lacks the inner capacity to handle change. So redundancy is about response. Diversity is related to response too, but not as directly. So if you look at organisms, so we'll go back to plants, if the environment in which a plant lives changes in significant ways, one way the plant can respond is simply by reference to changes in its genes. So mutations in its genes. Some of those mutations will be favored by a given environment. Some of them will be disfavored by a given environment. So my point is, that's an internal capacity within the system to develop different ways of responding to change. So both redundancy and diversity are supports to resilience. I don't think there's any great mystery there. Where the mystery is, in my opinion, and I haven't resolved this, and please don't take it to the bank. It's my own, I think, personal quandary. So I need to figure it out. But I've noticed that these principles, the 7 principles of resilience, I'm not always certain what they're supposed to be applying to. Do they apply to complex adaptive systems? Well, they're derived from an analysis of those systems. So they describe those systems. Fine. So they apply to those 2 complex adaptive systems. Now, the reason I bring this up is that is clear, but are they being used to describe ecosystem service systems? Because ecosystem services, this is, I find that phrase creepy. Here's another reason I find it creepy. Ecosystem services, well, how could they? I'm just not convinced I understand how these principles that apply to a complex adaptive system, how they apply to the SES, to the social economic system. Now, part of the answer to that question, it would appear, is at the end of this chapter. So in section 3.5, where they discuss applying these principles, how they can be operationalized. And they offer, I think, 6 recommendations, and you can take a look on 6 from 64 to 66. But these are principles aimed at SES management. So they're not aimed at ecosystem service management. They're aimed at social ecological management, system management. So what are they being applied to? Are they being applied to the ecosystem services, or are they being applied to the social ecological system? That's just a question that keeps emerging in my own head. So take a look at these principles: conserve and value redundancy, maintain ecological diversity. There are no surprises here. Build diversity and redundancy into SES governance. Now, that's a bit of a surprise, but I had warned you in the last reflection and in the one prior. Governance is here. It's lurking in the background. It's lingering as a kind of ghost, and it is now making an appearance. So these are not only principles, it would appear, of related to the SES, they're now also, in a sense, principles of governance. So my point is, these principles are taking on new layers of meaning as we march through this text. Now, I want to, if no one minds, I want to turn just for a moment to complexity science and read something aloud. I wrote it. It's not to be published. I'm not even sure it makes a great deal of sense, but it's about complexity science. Now, why end this reflection with a note on complexity science? Here's the reason. Just about everything in this book is derived or reflects what we can call complexity science. Now, what I wanted to say about complexity science is that it doesn't strike me anyhow, as a science. What it strikes me as is an amalgam or a combination of sciences added together. It's quite clear that these sciences, support one another in various ways within this type of literature. So you have, engineering science, sociology, mathematics, computer science, sociology, psychology. You have all sorts of people in this domain talking about resilience. But so the reference here is to complexity science. Now, as I just said, it strikes me as an amalgam of sciences, not a science itself. So it's not clear to me, for example, that we have a theory of complexity. And I would say as well, with respect to chapter 3, and this is why I'm bringing it up, they talk about how many of the arguments for redundancy and diversity rely on what they call theoretical arguments. The authors call theoretical arguments. At the same time, the authors they acknowledge that a lot of the reasoning behind diversity and redundancy lacks good empirical substantiation. So there's not a lot of empirical support for these theoretical statements. That's something I think we should keep in mind, and it bears on the issue of whether it would be right to refer to complexity science as a science. The way I see complexity science is this. Complexity science studies complexity in any scientific domain. Some of those domains have systems inside them that can be modeled on the complex adaptive system. But not all studies of complexity involve complex adaptive systems. If you know the field of computer science, there's a study of complexity, of computational complexity, which is core to the discipline. And it's a fascinating field, but it doesn't involve the notion of a complex adaptive system, because a computer is not a complex adaptive system. A computer is something called a deterministic finite state automaton. So I'll leave that with you. You can look that one up. It's a mathematical description of it's a model of computation, but it grounds the very reality of the modern computer. You know, the computer is a machine for us. For a computer scientist, a computer is not a machine. A computer is a formal description of a computational device. So computer scientists do not build computers. They study a finite, deterministic, finite state automata. So that's something you can take to a cocktail conversation, perhaps. With that said, I'll conclude. I didn't feel there was a lot of substance here that was surprising to us. So if you have any questions, comments of any kind, bring them to the Zoom session on Thursday, please. And with that, I'll conclude. I think that was a pretty fast one. Thank you. Take care.